Okay, here is a blank example. Okay, let's recall a classical problem. That is a bar, a thin bar, clamped at two ends. Both ends are fixed. Okay, so we have a thin bar, slim bar, both ends are fixed, and it is subjected to delta T equals 10 degrees Celsius. It's a heating process. Okay, so we just heat this bar by 10 degrees Celsius. Then based on the understanding in chapter 2, we know that this bar tends to be elongated, but it's not allowed because of the boundary condition. Right, so equivalently, it will be pushed, right, to keep its original length. Since it tends to become longer, but it's not allowed, so equivalently, we allow it to become longer, then push it back to the original size. So that you know that when you heat it, compressive stress will be generated in this bar, right? So based on this analysis and knowledge in chapter 1 and chapter 2, so we can solve it in some way. But that process analysis was a little bit complicated. So here, let's see how can we use the principles of indeterminate problems to solve this classical problem. Okay, these are what are given. So all conditions have been given. This delta T equals 10 degrees Celsius, and the modulus of elasticity, length, area, thermal coefficient of thermal expansion, all constants have been given. Okay, we're requested to calculate the stress in it. Okay, as I said, we can use these principles, these several steps, to solve indeterminate problems to solve it. Right. So our first step, free body diagram. Right, to find equations, the equilibrium equations. The second one, we will examine what the deformations will be. The deformations, correlations between the deformation and F and delta T. And the third step, compatibility. And then we'll solve it. Right, this is 4 steps. Okay, let's see the first step, free body diagram. We just cut it anywhere, just between these two ends. Let's just see, cut it from here, and then add the internal force outward. Let's see, it's just F. Okay, F. And here you should have, let's see, this is the point A, point B. Right, this is AX, AY, and the M, A. Right. So based on this, our equilibrium equation is just AX plus F equals 0. Okay. One equation, 2 unknowns. It's kind of meaningless, right? Cannot solve it. Then let's go forward. Second step, let's examine what is the deformation. Okay, the deformation. The deformation has 2 components: elastic deformation and thermal deformation. So the elastic deformation will be FL over EA, and that one would be alpha delta T L. Right? So this is just our equation, which is the expression of the deformation of this bar. And then the third step, compatibility. Compatibility equation. What is the compatibility of this bar? Since we have only one bar, one delta, right? But what is this delta? What is the value of the delta? This delta. It is delta equals 0, right? So this is our equation. Equation 1, equation 2, right? Just substitute this equation into 2. We will get the L is gone. The L is gone. This is just delta equals 0. So just F over EA plus alpha delta T equals 0. Okay, since EA is known, alpha delta t are also known, so that f can be solved. Right? F can be solved from these constants. Okay, so you can see that using this principle, these 4 steps to solve indeterminate problems, we can solve this classical problem about temperature changing.